Welcome to Beyond Longevity, the podcast that explores not just how we age, but how we can build a longer, healthier future for ourselves.
Why do some people develop heart disease, cancer, or diabetes decades before others? Why can two people of the same age look equally healthy on the surface, yet have completely different futures ahead of them? And what if one of the most important drivers of aging is something most of us are not measuring at all? My guest today is Nikolina Lauc, CEO and co-founder of GlycanAge. Nikolina works in a field that receives far less attention than genetics, hormones, or even epigenetics. Yet it may help explain one of the biggest questions in longevity: why some people seem to age faster than others. Her focus is glycans, complex sugar structures that help regulate the immune system and influence chronic inflammation throughout the body. In this conversation, we explore whether inflammation is merely a consequence of aging or one of the forces driving it. We discuss biological age tests, stress, menopause, hormones, exercise, longevity inequalities, and why some high performers may be quietly paying a biological price for success. We also tackle a fundamental question for longevity medicine. If we can identify risk 10 years before disease appears, what should we actually do with that information? Nikolina brings together deep scientific expertise and a practical understanding of how these discoveries might one day reshape preventative healthcare. Hi, Nikolina. Thank you so much for joining me on Beyond Longevity today. You are CEO and co-founder of GlycanAge, a company that grew out of your father, Professor Gordon Lauc's work in glycobiology. Glycans, to my understanding, are macromolecules of life, along with protein, lipids, and I think nucleic acid. But let's start right at the beginning. What is glycobiology and what are glycans? What do they do and why do we need them?
That's actually a great summary and introduction. So I think that's usually what we would explain, that they're one of the four building blocks of life. And my father was fascinated by them since I think he joined the lab when he was about 1920, and he worked really hard to get into this lab. And there, his boss at the time, he just got some new tools to look at this part of biology. So he gave them a task. And I think that was his first experience and his last life passion onwards. But they're complex carbs. And usually because they're complex sugars, we confuse them with other sugars that we're familiar with, like the sugars in your coffee, or this process of sugars damaging your proteins, destabilizing them. What we see is elevated HbA1c and then diabetes, but it has nothing to do with it. There's this other sugar language we have in biology that actually makes our molecules functional. So on proteins, when we look at them on antibodies, they would make the antibody more pro-inflammatory or anti-inflammatory, and our proteins would not be fully functional without glycosylation. And majority of proteins, or all the proteins we've invented since multi-cell life, are glycosylated. So they're designed to interact with us, with the whole system through this glycan language. And all of our cell-to-cell communication happens through glycans. So they're a complex sugar language that allows us to be multi-cell. If we didn't have glycosylation, we would still be single-cell bacteria. So they're an evolutionary step we needed to become more complex, and their magnitude's more complex than the genome or the protein.
You've already touched upon it a little bit, but not everybody listening is a biochemist or really familiar with the biology. We have a lot of investors and all that who know a lot of things, but might not really know about glycans. So just break it down a little bit more if you can. Where do glycans sit in the wider biology of the body? You mentioned they are involved in immune function, inflammation, and cell communication, but if you could just explain it, a little bit more, that might be really helpful.
They're absolutely everywhere. as long as you look. Maybe one thing that everybody is familiar with is blood groups. So glycans on blood cells would give you a certain blood group. And that was actually the first tool we had in personalized medicine 150 years ago now, that we learned that we have to give the right blood transfusion, otherwise you can even have fatality. So they're everywhere. Even conception is mediated through glycans. So there's these very anti-inflammatory glycan structures called sialic acid, which would coat a sperm to evade the woman's immune system and reach the oocyte. So they're everywhere. As long as you look, you're going to find glycans. Now, where we focused on and where we see the most significant role called inflammaging is in antibodies. So there, where we look at the strongest associations with age, it will be glycans and antibodies. There's, of course, many other glycoproteins. We look at many other glycoproteins in research. And if we look at diabetes, we look at total plasma glycans. So there's a number of different glycans from different proteins, more produced in the liver. And on the immune aging, it's all specific to antibodies or immunoglobulins. That way, the structures there regulate low-grade systemic inflammation, or something that now we have consensus that inflammation is one of the key drivers of systemic aging. So that's the one we specialize in. That's the one where we have the most work. And where there's also the most understanding of what these glycans do, but the best-selling drugs are monoclonal antibodies. There, the glycans are key to make them fully functional.
Now that we understand a little bit more what glycans are, let's angle it a little bit towards aging. Why don't you draw the connection between glycans and aging?
So there's a theory of aging called inflammaging, which is now 25 years old. So this year, 20th of June, we have a conference we're organizing on the 25 years of inflammaging that's being opened by Claudio Franceschi, who coined this theory of aging in the 2000s, where he categorizes it as what's a signature of aging is this low-grade systemic inflammation. Doesn't need you have to have a disease, but as we get older, we have this prevalent, constantly active inflammation, but also that inflammation can be a driver of accelerated aging. Now, the field of aging biology and finding measures to give us a clock of aging was very focused on what's happening within the cell. So early on, the research was oriented towards telomeres, which are specific to aging of a single cell, but they don't apply so well to the system. And even the hallmarks of aging, the paper from 2015, looked at everything that's happening within the cell, but they didn't focus on immunology. And they didn't acknowledge inflammation as a driver. They thought that it was a consequence of DNA damage, mitochondrial dysfunction, senescence. They didn't really look at it as a driver. And now we understand that inflammation is actually a driver of aging, not just a consequence of some of these processes. And then how glycans fit into it. Glycans are the key molecules we needed to become multicell and for our biology to communicate. So they're a key piece of information that we were missing to understand what happens on the level of a system, especially this fine-tuning of our immune system.
So what can glycans show us that standard inflammatory markers may miss?
Very good questions. Especially in the last couple of years, we want to compare performance with prediction of certain diseases, of general morbidity, so time to disease, and time to mortality. So we've just had a few papers come out of it. They're preprints, and there's one. We showed that accelerated GlycanAge correlates with some of these markers of a healthy lifestyle, some of them routine biochemistry. But then last year, we did a study with the UK Biobank where they modeled the mortality predictor on top of all the different measures, blood gut biochemistry that was measured in the UK Biobank, but it's one of the most comprehensive data sets we have. And then they were modeling prediction of mortality with that, or with glycans alone, and this is just glycans and antibodies, or combined. And glycans alone outperform prediction of all-cause mortality compared to hundreds of different blood biochemistry markers that we measured in this data set. And then when you combine it, you can even improve the mortality prediction. So they're complementary to what we're doing with this kind of routine biochemistry, but they are capturing a different driver of mortality related to this low-grade chronic inflammation that we don't get with CRP, because CRP was in this data set, and we had many studies comparing CRP, and it's more related to acute. And these glycans would be regulating how these antibodies, so it's more how the protein is regulated versus just a level of something that's a proxy for acute inflammation. And then we had another study, which was just looking at the changes in the glycome compared to changes in routine chemistry. And we see that your glycome can be altered up to 10 years prior to your routine blood work telling you that you have a problem or you being diagnosed with a disease. They're much more preemptive of a problem because everything we've designed for healthcare now is focused on identifying disease when you're already symptomatic, where we're trying to pin down what disease you have, versus preempt that you're heading towards a disease and measure that on an early molecular level. So glycans are opening this window to tell us, hey, something's changing, but we still have potentially a decade to do preventive healthcare. So we outperform prediction compared to routine blood work, and we capture a layer that's not currently captured with other blood work. And we also know that each extra year, so there was another study where it was a review, we combined 42 different studies that were done so far by our group, and we had 4 large cohorts in aging, so healthy people who are just aged without disease. We had 19 disease cohorts, and we had all-cause mortality cohort. So there was this 5,000 people from the German chronic kidney disease cohort, and every extra year of glycan aging, or think of it as immune aging, was a 10% increased risk of all-cause mortality, which was independent to CRP, BMI, different kidney markers, all of the known mortality metrics that were measured there. So we capture a different signal for all-cause mortality. And in comparison, similar studies have been done with the epigenome and different epigenetic clocks trying to do the same thing, and they did not outperform routine blood work. So we are capturing something that's not accessible with the current methods we have.
You've touched on quite a few topics that I want to delve in a little bit more. But let me just go back a little bit and go back to your father's research. How did you realize that your father's research could eventually become the scientific foundation for this company that you've created, GlycanAge?
He was convinced for a very long time. He told me he found a measure for aging on a molecular level more than 15 years ago, even 16 years ago now. So I'm 35 this year. I was 19 when he first told me about it. And then he had an idea that this could be something that can benefit people, or having this information can help us change healthcare. But there was no longevity market. There was no preventive healthcare hasn't been labeled as longevity medicine. It just, the market was very nascent. So there was no place to apply it. So the only place he could apply it to was a research tool. And they spent the next decade exploring this as a research tool to see what interventions move the needle, how does it behave in different environments, and how does it compare to different things we can measure. We did lots of GEVO studies, so we have lots of multi-omic cohorts. The first large-scale study they did and they were the first in the world to look at the human glycome at scale. In 2006, they looked at 1,000 glycomes. Now we've looked at more than 300,000. So it's a huge data, which is more than 80% of the global glycan analysis was done by his team. And they have 60 full-time scientists, 35 postdocs working on the topic of glycobiology full-time in different divisions, neuroglycobiology, cardiometabolic, many different divisions. So he knew about this for a long time. And I was a serial entrepreneur. So I started my first business when I was 18, or is legal to register a company. And I've had startups were quite successful even while I was still in university. And he was teaching me that this should become a company, or that we should start a company. But I was in a different field, and I spent a decade in tech, basically, tech startups, and then agreed to do this with him somewhere around 2020. We could have started earlier, but I think that having a few successes from an entrepreneur Stanford behind me helped, especially this dynamic father and daughter. I think it's nice, he is expert on his topic, I am on mine, and it's usually a good combination to have somebody technical, which in the tech world was a CTO, and a a commercial driver in the scientific world. It's a chief scientific officer and a commercial driver.
It's lovely. And it's also, intergenerational. And I think everybody brings something different to the table, which is very important. And that's what I think a lot of longevity companies actually are missing. A lot of them are very research-based and they don't really have the market know-how. So they never sort of make it off the ground, which is often a shame because the research is very solid. So, yeah, I think you're looking at it the right way.
You have this valley of death from when some things, you have a nice academic discovery and then that getting to market, most technology dies in this period.
Let's talk a bit more about this GlycanAge test that you're doing. When people hear biological age test, they may assume it tells them how old their whole body is. But I think aging is not a simple process. So I just want to get a very clear idea of what GlycanAge actually measures. Is it whole body aging or more specifically, immune aging or chronic low-grade inflammation? What exactly is it measuring?
Yeah, so aging will never be one thing. So there'll never be one hallmark of aging. And even in this initial hallmarks of aging, that was just focused on what's happening within the cell. There were 13, and now they expanded that. And they believe there's going to be many more. And immunology was not really a focus on it. Now it is. Where we fit into it is inflammaging. And there, even 25 years ago, Claudia was talking about glycans as being one of the key measures of inflammaging because they regulate the immune system. And majority of our chronic diseases has chronic inflammation as a key driver. And that's from cardiovascular disease, diabetes, cancer, neurological, pulmonary. All of it is related to chronic inflammation. And there is studies published on that 3 out of 5 deaths are related to chronic inflammation or diseases driven by chronic inflammation. And then they also did an interesting study where they looked at aging in different systems. And 52% of all-cause mortality was just related to immune aging and brain aging. So I can't say that this is everything in biological aging, but it is a key component of chronic disease development and this aging related to our health. Will it double our lifespan if we can have an immune system of a 20-year-old for 100 years? We don't know. No, nobody's done this experiment, but it is a possibility as we start to understand the markers more.
The longevity world has become very attached to biological numbers, I feel. The harder question with all this is, does this number actually tell us anything useful? And does knowing your biological age actually matter?
Well, we've shown that, yes, it will tell you a lot more than anything you can do in the hundreds of markers you can analyze from routine blood biochemistry. And it does outperform the other omics in mortality and morbidity. So it's certainly catching a signal that you can't capture in anything we're measuring so far. So it does give us a piece of information that's missing from the whole puzzle and is significant on its own. Now, does it matter for you as an individual? Will it change your future health if you know your age early? So that's data we're collecting, but from the last 5-6 years on the market, yes. On average, we see all of the people who retest within the year, they see 92% of women decrease their biological age by 3 years and 61% of men. I don't know why there's a gender difference, maybe stubbornness, but we do see that knowing this information changes behavior early, and we haven't shown that each of these extra years is a 10% increased risk in all-cause mortality. And we have some clients who move their immune age by 30 years. So that's a significant reduction in all-cause mortality. And obviously, there's different drivers in different people. And I think the key challenge we have as an inflammaging biomarker is that it can vary a lot from age. There are other markers which are usually much closer to your chronological age. So they'll tell you that you are maximum 5 years younger or older, while our marker can be 20 years younger or older. And actually, the average is 9. So the average we see in the data is you're 9 years older or younger, which makes sense from an immune agent perspective, from an inflammaging theory, and we can get into details of that, but also from a life expectancy. Because we have a huge gap, even in the UK, it's 17 years from Richmond to Blackpool. And there's a key factor contributing to that. And the age that we develop disease varies greatly. Some people get to 122, if we believe the record, and some get to far less than that from inflammatory diseases. So yes, I think knowing this information early will change outcomes significantly, but that's a piece of work that's going to take us a decade to collect and then prove out as a health economic saving.
You just mentioned there's a huge discrepancy in the life expectancy in the biological age and the chronological age. What do you think that is down to? Is it to the inequality of having good healthcare versus bad healthcare, looking after yourself, being able to afford expensive interventions?
So socioeconomic status plays a key role. If we do these large studies, that's the key conclusion we come to. And we've done a study of 31 different populations around the world, and the largest, it will correlate a lot with life expectancy in a certain country, but also the development index of a country. So socioeconomic status plays a big role. But then if you go to blue zones, that's not the case. They have low socioeconomic status and they have high longevity. So I wouldn't say that this is the main factor. And the problem is when we draw these averages, they never apply to an individual, because in the same cohort of people that live in Richmond, you can have someone who has a heart attack at 42. It might be more prevalent in a different location, but it still happens. So I think there's always an individual factor there. And I think one big factor that's going to come out more and more is chronic stress. And we also see that hormones are a strong influencer of that. But then again, this all potentially goes into this one complex system of our psychology, our nervous system, endocrine, and immune system interacting to govern our fight or flight, or to adapt us to our environment. And if you are living in a place where there's more stress because of a multitude of reasons, you are in this chronic stress space for longer. So I think that will be a key piece of the puzzle.
If chronic stress is a major factor of premature aging, should it not also appear in the very developed countries and the very wealthy people amongst managers and CEOs? Because obviously there's different stress and the body doesn't necessarily know, is it good stress? Is it bad stress? Is it stress because I don't know how to afford my next meal? Or is it stress because I don't know how to make my next million? So how do you see that?
I think it's really interesting. And I think that that's one of the studies we have to look at the impact of stress. And that's a 10-year study. We're in year 2 now. So I can tell you the first couple of years what happened. But let's take examples of PTSD, ADHD, more these kind of, I don't want to say mental health disorders, but let's say deviation. And if you are diagnosed with PTSD, on average, you live 15 to 20 years less. And that goes for every mental, even ADHD, you live 8 to 13 years less. And it's not that these individuals suffer from anything unusual. They get all these chronic diseases much earlier in life, cardiovascular disease, cancer. And we could categorize all of that as an altered stress response. Only PTSD has stress in the name, but all of them are an altered stress response. So I think that's the proof we have that stress can age us prematurely. But obviously, it's a really hard thing to define because two people can have the same stressor and have a completely different response to it. And I think that's where we unpack some of these complexities. And what we've identified in some of the clients were early on is there's a certain signature. And this was back in Claudio's theory, where he was explaining the stress can be a driver of aging. So you can have a young person who's highly inflamed because of stress for different reasons, that's still healthy, but is heading towards inflammatory disease and mortality earlier because they're accelerating this process. And that's, for example, what we see in athletes. We did a nice study of over 1,000 people where we had different cohorts of professional athletes, moderate exercisers, people starting to exercise, sedentary overweight. And we saw that the professional athletes have the same levels of chronic inflammation as a sedentary overweight because of the physical stress. And they also have shortened life expectancy. I don't have this stat here, but there's a type of athlete which has the shortest life. I can dig it out, maybe share it with you afterwards. But it's incredible that these ultra healthy examples of health actually are not achieving longevity. And there is potentially this driver of the physical stress because they're paid well to wreck their body for performance, which they can do for a limited period of time, but then the body fails them or gives up a lot earlier, 35, 40. This is, you're not supposed to retire at that age. So I think that's physical stress where you have high performance and you have high socioeconomic status, but you don't have longevity. And I think this also applies to certain executive profiles. And that's what we started this study to look at the impacts of stress in something we're calling the biological cost of entrepreneurship. It's something I'm interesting, but I think it applies to all high performers. So we will probably have to look at many other high performers. And we're looking at the entrepreneurs, investors. We thought there would be a control, but actually they're also coming up with high stress profiles, and corporates in cushy jobs like Google executives. And we're following them for 10 years. And there's this interesting pattern that the founders of the companies that are the most successful, or some of the biggest companies in the world, had reduced longevity. And here, think of Steve Jobs. I think he was 56 when he died from cancer. Walt Disney died at 65. You have all the money in the world, and you don't have longevity. And then you have another cohort of successful founders. And think of the Dell founder, Bill Gates, Amazon, where they are achieving, hopefully, that longevity, or they don't have this early mortality. And there's some historical examples as well. So it's not necessarily that this kind of high stress environments for building the most ambitious company in the world will lead to early mortality, but there does seem to be a risk factor there. And it does seem to be a prevalent archetype for high performers. And that's actually what we see in the signatures, that you can have 35-year-old, early 40s that has no diagnosed disease, normal BMI, maybe only hormonally, metabolically, they will have some early dysregulation, but their immune age will be sky high. It could be 20, 30 years above. And I think that potentially comes from being stuck in a type of chronic stress response that comes from early childhood stress, where although the environment has changed, they have not adapted. And this doesn't mean that everybody who has this early childhood stress will have this outcome. It just means that there's a vulnerability. And I think some people come out of that and some people get stuck in it. But that's a big topic. So.
Oh, yes, absolutely. Measuring biological age. There are different aging clocks around, like epigenetic clocks, like Hover style, DNA methylation, blood biomarkers, loads of them, including glycan clocks. I would like to understand what each one is measuring. And do we need all of them? Do we need just one of them? Should we use all of them? Or is that too much information? Where do you sit?
I think every hallmark of aging will be relevant for some things. And we will all age in different ways. Now, it depends on what criteria you use to categorize them as a successful aging biomarker. And then also how they prepare to things you can already do at your doctor. So I think we've shown that from a glycan perspective, this outperforms current biochemistry. So epigenetics did the same. There's research looking, and that's using all the clocks, first, second, I think maybe even third generation. I can share the paper if you like. It just came out in preprint. And they didn't outperform routine biochemistry and other known risk factors like BMI. So they don't necessarily give you more information than what you can currently get your doctors, or just the kind of standard risk factors that we know. Could be due to the model. Maybe these models will improve. I'll share the paper. You can look at the ones they evaluated. I think it's most of the ones which are on the market now. And then the other criticism that this space gets, and that goes from telomeres to epigenetic clocks to even some of the blood biochemistry clocks, is this variability. So if you measure in the morning and the evening, are you going to be significantly older or younger? And here, telomeres had a huge variability issue. That's why they never became a successful measure of systemic aging alongside their aging of a cell. And that's relevant for certain things, but not maybe as a general marker of biological age, because they're supposed to be surrogate endpoints for clinical trials, but also for us as individuals to tell us, hey, I've made an investment in my health. Will it pay off in the long run? Is this new diet I'm trying? Is this new intervention actually giving me value for the time, money that I'm investing there? Because otherwise you have to wait 20, 30, 50 years to get to the outcome and learn if what you invest in your health is actually going to pay off. So there are feedback mechanisms. Telomeres had the variability problem, so you can't really see impact of an intervention because of the variability. Epigenetics have a bit less of that, but it's still 5 years up and down. So if you, even 7 years, in 10 years in certain clocks. So if you send your sample in the morning, you send your sample in the evening, you'd be 10 years up and down. And we've shown stability ourselves, but then we did an independent study with Mike Snyder from Stanford, and our variability was less than 1%. So if you see a change in your age, it's not the measurement error, it's an actual biological change. And then we also had an interesting study that's not published yet, but it's a known experiment in the field where Jamie Haywood from Alden Scientific sent 250 blinded samples to a number of aging biomarker companies, including 30 of his own samples that were taken in the same day or same few weeks. And his epigenetic age was 10 years up and down on the same day. And his GlycanAge was plus minus 1 year, 4 months, or this whole period. So we have this ability to apply to an individual to give you feedback. It is predictive or mortality and morbidity more than the things you can currently measure. And I think we can claim that it's a good investment for your money. I would say the criticism we get is that your immune system can be much older or younger. But from an inflammaging theory, that's exactly how it should behave. And it's more this perception that we have around aging that when something tells you that you're 10 years or 20 years older, so you're 30 and your immune age is 50, you might not necessarily feel 50 because you're not in that stage you have symptoms or that you feel the aging, you're driving the aging. So then we have this complexity of being able to explain it to individuals and say, hey, yes, you don't feel it now, you feel great, you're in fight or flight, you're in chronic fight or flight, you're functioning amazingly, you're a high performer as an athlete or as an executive. But actually, you will pay. You're in the future. You'll come at a cost. And doing some changes now, which actually most of it means more rest and recovery. That's all. It's stepping back, which is harder to do than to recommend for certain people, has a significant impact. I'll give you an example of a client because it's a very nice. It also contradicts what we see in research because we did a study on HIIT training in a cohort of men who were 35 who were former athletes. So they did sprint training in 12 weeks, and we see all of their glycan become anti-inflammatory. So their age goes down in 12 weeks. Then we have this customer, executive, early 40s, 2 small kids, high-profile job, and does HIIT training every evening. And her age was 17 years above what it should be. And then her practitioner did one change. She was like, we can't take away the kids. We can't change your job. You love your job. Can we change the HIIT to yoga? So instead of you piling on physical stress on top of all the mental stress you have in the day, can we switch it with something that will still be a physical activity, but will give you less impact? And she changed to yoga. And within the 8-week follow-up, she went down 13 years. One change. That's the key. It's trying to find what is causing you damage before you actually have a problem. And then although you're doing something because you have a good reason for it, you want to be fit, you want to do it all. Maybe it can come with some compromises which don't cost you as much. Like yoga is still a good type of exercise to do, but will pay back a lot more in the future.
Do correct me if I misunderstood what you said or misinterpret what you said. Are you really saying that most of the epigenetic clocks that we have are really just a snapshot of how we are at this moment in time? So if we've slept badly or had a fight with our child and it caused us some stress, does that immediately reflect on the result or not?
No. So there are studies that show exercise can alter it significantly. but we don't mechanistically understand what's driving the epigenetic clocks. That work hasn't yet been done. So we're not clear on the mechanism. From glycosylation of antibodies, we know it regulates inflammation. Because of all the smart drugs, we exactly know what each glycan does, and they're functional effectors. They're not just information, they're active molecules. So we can say there it's regulating inflammation. That's the mechanism. For epigenetic clocks, we don't know that. I think that work needs to be done. And I think the variability will hopefully be fixed with a better method, because right now everybody's relying on the Illumina array, and it was designed for research, for cohort analysis. So when you do a large cohort of thousands of people, you're going to find very interesting signals. And this variability is up to 10%. But if you apply this to an individual patient, that means that there are 10 years difference, which doesn't help you evaluate if a certain intervention is actually moving epigenetic aging or not, because the measurement error is larger than the impact of the intervention. So I think there's a technical problem there, and epigenetics is a very valuable omic. I don't want to speak badly about anyone, but I'll show you the papers that we've done for that. They're published here. There's one interesting one in the preprint now. So I think that needs to be resolved for them to be applicable to an individual patient. And then the other thing that needs to be resolved is this outperforming tools we already have. So I think there's two criteria there where I wouldn't be investing my money. I would invest in other things, but I'm not yet convinced on these things.
So do you think the most useful assessment might be to combine different clocks with functional markers such as strength, VO2 max, blood pressure, ApoB, I don't know, all those things?
So we know that clocks you can derive from routine blood biochemistry, and this is kind of like the epigenetic phenoage. It's a proxy for routine blood biochemistry, but just from epigenetics, which is more expensive to do and more variable. It is useful. So if you combine glycan and that data, you get better prediction, and it's different signals. So it's giving you a perspective from different signals. So that I would do as a good combination. And even in the study, we did a combined clock that combines your blood biochemistry clock and your glycan. We didn't commercially launch that as a clock yet. I think here we're still debating what to do with that information because it is closer to age. But the challenge is when you look at these things in a combined clock, there was another study that was done a few years ago that did all the omics and all the different clocks from the omics, and then compiled it all into a clock they called the mega omic clock that was perfect in predicting your chronological age, had zero prediction of outcomes. So when you combine too many things, you get a marker of chronological age, not biological age. And you will have different driver in different people. Maybe inflammaging, the GlycanAge will be a key driver of a problem for you, but maybe something in routine biochemistry will be a key problem for somebody else, and other markers as well. So I think some things make sense combining, some we need to wait for better tools and more data.
But is that not very hard for the consumer these days?
Yes.
There's a lot of choice and we don't know what to measure. And also often when we do measure something, we don't really know what to do with it. When someone comes to you and takes the test, what is the exact process? So first of all, what exactly do you tell the person that comes to you with their result? What exactly are they then to do with it? And also, is a long-term tracking not more, I wouldn't say necessarily beneficial, but more helpful in telling a person where they're going and what their outlook is, rather than just a one-off test?
Yes, ideally you track it long-term. That's the hope, to see what's happening through time versus a single snapshot. So I think whatever clock you commit to, track it longitudinally and track it before and after you do a major change so you can get that feedback if that's worth continuing. And that can be a new exercise regime, a diet, a therapy, a supplement, to know that this investment is going in the right direction. From our test, we don't want to claim anything that we don't have substantial science for. So I think there's a lot of tests that put a lot of information in there which doesn't necessarily go in line with the evidence. And that's especially on the interventions. We have very little evidence on intervention. We can start to distinguish not just where your immune ages, we have a marker of immune resilience. So this is based on the studies we had to predict mortality, morbidity. This is way in advance of a problem, so it's better to translate it as your resilience to future mortality and morbidity. And then we can start to distinguish because we look at different types of structures there. Some are mostly related to hormonal deficiencies or autoimmunity or cardiometabolic changes. So we can start to distinguish where is inflammation coming from. So what is your key focus area and where will it go? And then it will be different advice for different contexts. So if you are in perimenopause to menopause, estrogen has the most predictable impact on reducing your GlycanAge. And that's in all the studies we've done. Of course, dosing matters a lot and timing also matters. If you're overweight, we have an enormous amount of data on caloric restriction, different diets, bariatric surgery, now GLP-1. So if inflammation is driven by excess weight, there's a very clear intervention, then they'll have the most impact. And then for some, it's autoimmunity, which you would manage in a different way, or the stress profile. This is something we call the manager's profile. Yes, there could be some early hormonal metabolic disbalances, but this is generally still related to the chronic stress. So you don't need to replace the hormones, you need more rest and recovery. So it would be different interventions for different people. And as I said in the example, we have AI doctor. So there's alongside the report, there's an AI doctor, but we still have the human consultations as a part of the service, which is free of charge. And it's with every test because we find that this human consult has a much better impact on behavioral change, especially when you talk about human problems. So I think AI can give you a lot of insight, but for some reason, after you talk to a doctor, the likelihood of you acting on that is still a lot more. And I'm waiting and we collect our own data, I'm waiting for that to change. And some people do prefer to talk to the AI than to a human. But the ones that do talk to human, we see a lot more impact on their.
Yes, other guests that I've had on mentioned that as well, that the human interaction still has a big impact on people actually changing their behavior. So I do think that that is a very important part of what you do. How often should people test? Because it obviously takes some time for the body to adapt and to show the results. So is it twice a year, every month?
So the half-life of what we measure is 21 days, and we wouldn't recommend earlier than 8 to 12 weeks. That's when you can see a full change of something that you've done. And this is only if you've done a change. If you haven't done any changes in that period, you'll be getting the same date. So we don't recommend retesting until there's been a significant change. Once a year or twice a year is usually the optimal cadence. And then if you have a good result, once a year is sufficient. When you are starting a significant change, some things take longer to show you a beneficial effect. And we know this from weight loss, especially combined with exercise. We see that if you are doing a lot of physical activity combined with caloric restriction, actually you become pro-inflammatory in the first couple of months. And then this changes after 6 to 9 months. So when we had a big cohort of around 1,000 people aged 40 to 60 going to the gym for the first time from a sedentary lifestyle. And it took them 9 months. First, they became slightly inflamed. That stayed for about 9 months. And then they started to become more anti-inflammatory. And we see the moderate lifelong exercisers. Women are 10 years younger on average. And I think for men is 7. I have to double check. But so moderate exercise, moderate lifelong exercise has a big effect. But if you're going from a sedentary lifestyle into the gym 3-4 times a week, it will take time for your body to adjust. So then depends on the individual. Some want to see the progress through the year, so they want to see it go up and down. Others just want to see good news. So it also depends on your psychology. Are you prepared to see the bad news? And this is the same with pregnancy. So something really interesting happens within pregnancy. Even if you have a very high GlycanAge, it goes to the floor, which is 20, because we see the immune system is mature post-puberty and then starts to age. This period before is also interesting, but it's more complex. So we see that even rheumatoid arthritis goes into remission in pregnancy. There's a special estrogen that women create during pregnancy that seems to even put some autoimmune diseases into remission. And then post-pregnancy usually age upwards. about a decade on average, and then you recover post breastfeeding. So some women like to track this whole journey. They want to see how much is going down. They want to see the impact before and the recovery. Others don't want to know for a few years after. So it depends on what type of news. I like to know all of it, and some people we know do all of it, and others they only want the good news, and they struggle with bad news.
The age of a mother does go down once you've given birth, and then let me tell you, it goes drastically down again once your children hit puberty. So, yes.
You mean it goes up?
Sorry, the age goes. That's exact. Sorry, I mean your life expectancy goes down, is what I should have said.
And actually, that one's more complex because especially moms who have kids late, they seem to live longer, which is probably a predisposition. But we see full recovery after a period. But yeah, it is the best stress test for the body. And it also preempts future problems if you don't do well on the stress test.
So you've mentioned hormones. What evidence suggests hormones and GlycanAge correlate, or that there's a connection? And what can we learn from it? And do we have to be careful not to overvalue that result?
So hormones, same as in pregnancy, the special estrogen lowers GlycanAge for a majority of women. Menopause accelerates GlycanAge. In all the studies we've done, when we compare men and women, they have different aging curves. So men are a straight line going up with age. Women, much slower. They're usually youngest. And then you have this acceleration, 45 to 55. And they do also have less chronic disease prior to menopause. And they seem to have this more anti-inflammatory. So that's maybe even the response to cold. Maybe there's a reason there's the man flu. Maybe they actually have a stronger, But we experience it differently. So we don't understand each other's perspective. So we do see women are more protected against inflammation prior to perimenopause and menopause. And that's in all the cohorts. So that's 300,000. And I think we have good gender proportion in all of them. And then in twins, we follow them longitudinally. So that's a Twins UK. We had them premenopause, postmenopause, and we see that this rate of aging, perimenopause to menopause, doubles. And then we had very nicely designed trials where this was done by Harvard 20 years ago, where they suppress hormones. So the same therapy you go with IVF, but they knock your hormones to the ground for men and women. And then they give them replacement or they give them placebo. And the ones that get the placebo age 10 years, within 6 months of hormone suppression. And the ones that get replacement do not age from immune system, from a GlycanAge perspective. So hormones are one of the greatest modulators of the glycom. And that's also in men and women. So they did the same study in men where they knock testosterone to the floor. They give them back replacement, or they give them replacement plus aromatase inhibitors that blocks conversion to estrogen. And we see that the ones that block conversion to estrogen become inflammatory. So what steroids are, or this kind of bodybuilding community, they usually block aromatase because they're going for very high testosterone to build muscle. And we see that will be very pro-inflammatory. Well, if you have naturally lost testosterone because of aging, which happens to all of us men, then replacing that, what you've naturally lost, seems to keep the immune system in balance. So I think there's a dosing element here. And there's also we don't have a lot of personalization in hormone replacement. And actually, we have now ongoing trials to evaluate this as a marker for dosing of hormones in men and women to optimize for what is the right individual level for a long-term outcome in an individual. That's one application where hopefully we'll have personalization of intervention. We're doing the same with GLP-1s, all versions, even the new ones. And I think stress will also be an interesting category to personalize.
And I think it's very important just to really clarify and sort of highlight what you just said. Hormone replacement therapy, all this testosterone, it is not to go over your natural testosterone level, but just to bring it back up to where you used to be. So I think that's really important to point out.
We don't have long-term data on men. So I think that part is missing. It's interesting that we see actually the estrogen, so a healthy level of conversion of testosterone to estrogen in a man. So that I think that needs an interesting long-term evaluation. I can talk about a cohort where we have some data on estrogen in men. But first on women, there's data for now. You have 56 years of data on women on, not on HRT. And early in menopause, it reduces all-cause mortality by 40%. So if we're talking about longevity drugs, where we have the hard data, and that's coming out in all the long-term evidence we have. Even the UK Biobank, they're looking at the drugs that have the most impact on health span and lifespan, and estrogen there was several types of estrogen which came up there at the top. So I think that is a longevity drug that women have, and it's probably what keeps women alive for longer. And yes, we have more disease post-menopause, but that's probably because of the loss of our ovaries. And then for men, there was an interesting cohort we have. I usually say it as a joke. There was this famous scientist, I won't name him now, but he had a joke to say the best thing you can do for your longevity is be a woman. And then I said, like, actually, there's a better thing we can say. We had this data from a HIV biobank from the US, the largest biobank. It was followed over 15, 20 years, something like that. And you had a cohort of people born as male who went onto estrogen to transition or gender-affirming therapy. And that cohort was followed longitudinally, and their glycan became quite anti-inflammatory, almost did it mitigate some of the effects of the disease. And they had a long-term outcome change, which was less coronary plaque. So you see a change in a biomarker and you see an outcome change. And that's the evidence we need to gather, not just in this one cohort that won't apply to everyone, but in interventions that can apply to everyone that will have a significant effect on different mortality and morbidity markers.
Okay, now let me ask you a really basic but very important question. Why is GlycanAge testing not part of routine healthcare?
Whoa, this is our whole mission, and it's a very hard thing to do. First, the analysis is incredibly complex. So we started in this field, my father did 13 years ago. And then you were looking at a couple patients maximum, like 10. You would publish a paper with 10 glycans, and that would be a very hard thing to do. And then they went to thousands from 2006 onwards, and it's magnitudes more complex than genome proteome analysis. And it's an incredibly hard method to replicate in the labs. We've now set up two labs in the US, a lab in China. We're setting up a lab in the Middle East. And this transfer of method is incredibly complex because it's days of chemical steps. And we have it in 3 hospitals at the moment. And we're taking the method from 3 days of chemical steps, which is when you do double shift, to 1 day, which is incredible. Because in the hospital, they don't have time. Scientists have time to run an analysis for 3 to 7 to, it used to be 2 weeks of full work. So healthcare is not equipped for this type of complex analysis yet, and it will take us a long time to get it to a point that put your sample in a machine and an hour later you get a result. That is, I don't want to estimate, but a long way away, which is what you can do with a lot of routine testing today. So it's a complex assay that has to be run by a specialist lab. And that's one key preventer in scale. The other one is knowledge, having basic knowledge of glycobiology as something that's introduced, even as just additional education. So we do a lot of education and conferences where you get this continuing medical education credits for doctors who want to come and learn about inflammaging, like the one we have in June. And this is a way to motivate doctors to go and learn about something new. They have like a certain amount of credits they need to have per year to maintain their license. But raising awareness about it and educate about it, it's our key goal and our key challenge as a company. Nobody else is focused on it as much as us, because I think my father was the crazy guy. He's also the high achiever with a very high GlycanAge and not willing to do any psychotherapy yet. So maybe we need to invent some, new anti-inflammatory drugs that he's actually going to take, because, his key problem is the mind, that he's not willing to work on it. But it has been impossible. Like, we are the largest glycobiology group in the world, and we started hyperglycomics, and we have lots of collaborators. Leiden University is doing a phenomenal job also in scaling their hyperglycomics. But the mission is to bring this technology to as many labs, hospitals, scale it globally, and that's an impossibly hard task.
So what does the future hold for GlycanAge, and what are you excited about in terms of preventative health?
Depends where you categorize prevention. I think the prevention we do in longevity medicine and in the consumer side is very early. So you can be in your 20s and identify a problem early, work on it. Mine goes up and down a track yearly, but I still get back into the 20s. I have acceleration from chronic stress, which is mainly my psychology, which probably comes from my father. And then I find a solution to it. And of course, this is very individual. And sometimes it could be more rest and recovery. And sometimes it's a meditation retreat. And sometimes it's psychotherapy, depending on what's the right solution for what's going on. So I think in that space, we're doing very early prevention. This is kind of like the first signal of a problem. And then in healthcare, in the hospitals, we don't give them an age. Doctors are not ready to work. I'm talking about classical healthcare is not ready. They have no conversation to, if a test tells them you will have a problem in 10, 20 years, or we even have markers which are specific to certain diseases where it's like, hey, you have a certain likelihood of developing hypertension within 7 years. Doctor would go, okay, come back in 7 years and I know what to prescribe you. But up until that period, there's nothing I can do for you. So healthcare is a reactive system. It wants to go towards prevention. That's very small amount of prevention is a little bit of cancer screening, but we haven't really got there with other major disease categories. And there we did a lot of work on cardiovascular disease, where we've gone from retrospective to prospective randomized control. So we've done a lot of research on prediction of cardiovascular events, and we've gone from retrospective studies. We had one with 27,000 Germans tracked over 30 years. And then we did 2 really nice cohorts with Harvard University, TNT and Jupiter, where they had both primary and secondary prevention of CVD events. And then we replicate that in a Middle Eastern cohort, and now we're doing women's health. So women on HRT, not on HRT. And we see this inflammatory driver of CVD that outperforms CRP, LDL, and even statin use. So there is a driver of cardiovascular disease, which is this low-grade chronic inflammation that we don't capture in current routine testing. So that's now being developed with these 2 hospitals as a screening test. One of them is private, so we're doing primary prevention. And the other one is a public hospital where we're doing secondary prevention. So when you have your first heart attack or stroke, we screen you for the risk of the second one, where we have some route to reimbursement. And this is still categorized as prevention in healthcare. It's unfortunately secondary prevention. And then primary prevention is predominantly cash pay. And there is some employer executive checkups where this is the first market we can access. But I think this early prevention is still very much in the hands of those that can afford it.
Listen, Nikolina, we've come to the end, but I'm desperate now to have a glycan test myself because I've never done it. And I have to say, one of the reasons really why I've never done a biological age test is because it is a little bit what you've mentioned. I always find it's very sort of momentous and it doesn't really tell you anything about it. But I think I have been converted. I think I will do a GlycanAge test just to really see, if my children have aged me beyond my biological age or not. And you mentioned a lot of various research papers and all that, which I'm sure are really interesting to our listeners. So we'll put them all in the show notes so that everyone can look them up at their own leisure. And now I have some rapid fire questions, which I ask all my guests. What's the single best piece of advice you would give your younger self?
My younger self. I think I have had a good drive of making a bet on myself, but I would still do that without confidence in a way. So I think the main thing that's changed throughout the years is my confidence. Maybe there's some experience, but I think the capability was always the same. So I would just say that being a bit more bold would have gone miles for me.
Name one habit everyone should adopt for a longer, healthier life.
Sleep is still my number one. I can compromise on most things at time, but if I also compromise on sleep, I feel it more than anything else. So I think sleeping an extra hour for me is worth more than going to the gym for an extra hour.
If you weren't in longevity science, what career would you have chosen?
This probably evolved through time because I think I want to be a vet when I was younger, and I loved looking after all kinds of animals. And I think I translated that to looking after people. And I have 4 younger brothers. So I think this kind of care about people was always there. And I think the thing that's come out more and more is the psychology. So I think I would go into psychology.
What microdose habits, 5-minute routine, or small daily action yields outsized longevity benefits?
So I've always operated in a high stress environment, and I think this is normal with entrepreneurship, normal in many other situations like young kids. So whenever there is a short period of time to relax, and that could be slowly, sipping a coffee for 20 minutes, which is a very Croatian thing. Croatian, my bad. They would do it for hours. Take that moment. When there's a moment to relax, those little moments add up a lot. And if I don't have them, I feel it in a very different way.
And what's the craziest longevity myth you've encountered? And is there any truth to it?
Craziest longevity myth. From the things I've heard, there's nothing crazy anymore. I mean, there's so many incredibly crazy things, and you would need a whole other podcast to explore those. But one thing that we do see work, and we actually want to do more research on, is started with this young plasma research. So there was a scientist who tied these mice, or maybe they were even rats, to exchange their plasma, and the older mice became younger, the younger mice became older. So definitely we should not practice this in people. In the lab, they do crazy experiments. Later, they learned that even diluting plasma has a very positive effect. We recently did a study on therapeutic plasma exchange, and that had a long-term impact as well. So after, I think everybody reduced most reduced after 3 months, and in 6 months, there was a 3-year reduction on average, but it was 0.4 years per month. So that's a interesting therapy that's already being applied, and there it's more, they're not replacing it with young blood, but in some there's a very low dose of these antibodies that are from donors, and albumin. That's usually the cohort of donors there is young. It's not just diluting, there's other components to it. And then there was a study we got samples for where they were, and this is pretty wild, but they were taking plasma fraction from young piglet liver, I believe, as a therapy for senior rats, and they lived almost twice as long. So there is something in this young plasma, and also IVIG is used as a therapy for some autoimmune disease, and these are donated antibodies that work as an anti-inflammatory therapy and don't have some of the side effects of some of the autoimmune therapies. And the impact is long-term. It can be disease-altering long-term. So there is a component there where maybe can lead to some discovery of novel drugs we can develop to modulate that system without having it really complex. So I think young plasma is an interesting avenue where there's still a lot of work to be done to understand why it works, what works. And one avenue we want to explore is pregnancy, because there's something special, and especially just before delivery, it's in a way as if the mother is preparing the newborn with these anti-inflammatory antibodies to prepare it for the pathogens, for the food. And we did a study, a neonatal study of just born babies 2-year free. And there's this interaction that happens from the mother to the baby, and maybe even for breast milk, where we want to see what's happening with the antibodies there with glycosylation, and maybe even find some novel drugs that can alter that without needing, to be a newborn. But, nature has figured something out there from an inflammation standpoint that can give us clues on where to go with potentially some anti-inflammatory longevity drugs.
Amazing. Well, thank you so much for coming on Beyond Longevity. I had such a great time. Thank you.
No, you're welcome. Appreciate it.
That was my conversation with Nikolina Lauc, CEO and co-founder of GlycanAge. What I found most interesting about this discussion is that it challenges a common assumption in longevity, that measuring more automatically means understanding more. Nikolina argues that the real value lies in measuring the right things. In her view, chronic inflammation and immune aging may be amongst the most important signals we have, yet they're still largely absent from routine healthcare. Whether you agree with every conclusion or not, this episode raises some important questions about how we measure aging, how early we should intervene, and how much of our future health may be shaped long before symptoms ever appear. And perhaps most importantly, it reminds us that biological age is only useful if it helps us make better decisions. I hope this conversation gives you a sharper way to think about the numbers, the science behind them, and the limits of what they can tell us. Thank you for listening to Beyond Longevity. Please follow, subscribe, and rate. Thank you.